Okay, I guess it's time to get started. There is, as you can see, plenty of space. So if some of you want to move up, that would be fine. So my name is Peter Schlosser. I'm co-chairing this session with Liz Canwell and Robin Munch. And I just want to, as an introduction, want to give you a little bit of background behind that session. As you all know, or most of you know, AGU has developed a strategic plan over the past 2 years, and you might have seen these little sheets that has the major elements of it. And if you look at it, one of these bullets has to do with science and society. So we thought in our discussions in the Ocean Sciences Section Executive Committee that it actually would be nice to create platforms to allow exchange on topics in applied ocean sciences with direct relevance for society that could engage naturally members of the Ocean Sciences Committee, but also open the platform a little bit beyond that, and hopefully as we go along and build that into a session that becomes a natural part of our ocean sciences program, also hear from people who are using our science and tell us what they want to know from us. So in other words, include stakeholders in the discussion. And these stakeholders can come from the private sector, from government, from other decision makers, NGOs, and also we want to address, of course, the general public. We have decided to launch 2 of these sessions during this meeting here. One is this one, Sustainable Oceans. There is another one that is chaired by Rob Evans on coastal issues. And as a third element, I just wanted to remind you that we have this year, as part of the Ocean Sciences Section Luncheon, which is tomorrow from 12:30 to 1:30, a speaker who also talks about an issue that is of great relevance for society, and specifically Klaus Lackner will talk about how to stabilize or control the atmospheric CO2 concentration. So we offer that as a nucleus of a program that hopefully will grow and where members of the community will engage and propose their own sessions that really try to connect our science to problems that the stakeholder community has, and more importantly, start to build a dialogue where we actually hear from these people and not just preaching to them and hope that our science will trickle through and somehow they will find it. So the session is organized in the following way. We will have 3 20-minute talks on some key issues, and then 3 more regular 15-minute talks, we will lead through the talks in the typical way. Speakers will be introduced by Robin and Liz, and they also will keep track of the time. So with that, I will hand over to Robin to introduce the first speaker.
The first speaker in the session will be Hayo Eichen from the University of Alaska, and he's going to talk about a little bit about what's happening up in the Arctic Ocean and how we might deal with it. Here, I've got a usual collection of clip-on noisy microphones. If you put it right up here, it should be fine.
Thanks.
And here's your mouse.
Thanks, Robin. So thank you for the opportunity to talk to you today. The Arctic is an interesting place to look at this question of sustainable oceans and sustainable ocean use, in part because the rate of change that we're observing these days, both with regards to environmental change as well as socioeconomic change, probably is the most rapid anywhere in the world's oceans. And at the same time, of course, the Arctic Ocean is a region that, even though there's some history to exploitation, say if you think back 100, 150 years ago, whaling in the Pacific sector of the Arctic, there's some history of unsustainable exploitation, unsustainable use. But right now, with this rapid rate of change, we're seeing the system being stressed and tested potentially to its limit. So it's interesting to ask the question, what role in particular the academic research community or researchers with different agencies can play in this can play in this whole setup. All right. So Just a brief outline here of the talk. I want to talk a bit about sort of the institutional framework here that is of relevance, and I'll explain that a bit more. Talk a bit about what one might call the Arctic data paradox, and that really is a thread throughout this talk, is this idea that on the one hand, the Arctic is not a data-sparse region anymore, but at the same time, the way data are now being collected about the Arctic that are meant to serve both scientific researchers and the stakeholder community is really very much happening in a data rush mentality, where there's quite a bit of things that we need to think through a bit more carefully. And then finally, in order to do that, I'll talk a bit more about information and data as a resource, and how we can move to what you might want to call a regime of data co-management and data production. Now, first thing is I'll focus here on the U.S. Arctic sector, because that's an area where we have a fairly good background on what's available in the way of data, but it's also one of the regions where we see the most rapid change. And the other thing I'd like to highlight is the role of the diminishing Arctic sea ice cover, at least over the past few decades, that plays an important role here, where we see not just reductions in summer or seasonal ice extent that are very much different from what we've seen in the past, but at the same time, these opportunities that are created through a more open, more accessible Arctic for business interests, the private sector, but also at the geopolitical level, are resulting in this, what you might term the sea ice nexus, where a lot of interests are focused on a diminishing Arctic ice cover, but a lot of these interests aren't necessarily well coordinated. Some of them are in direct conflict. And so as a result, the CS Nexus is generating both new partnership, but also plenty of lawsuits at the federal and state level. And that is, again, part of this what I would term the Arctic data paradox that I'd like to look at a bit more detail. So in order to do that, the first thing that we found to be helpful, just as the Millennium Ecosystem Assessment did for the whole concept of ecosystem services, is go in and look a bit more systematically about what aspects of ice-covered ocean use are of interest to different stakeholder groups. And if you look at the services or the different uses the sea ice cover sees in this region, you have regulating services ranging from the role of the ice cover as a climate regulator or as a geologic agent, all the way down to some of the cultural services that relate to subsistence activities by indigenous communities, or even the use of the cultural landscape for tourism. And again, what's interesting is that all of these different services are now being brought into a space where they're interacting with one another, and where the intangible values that certain communities in the Arctic hold with regards to a changing ice cover are in potential conflict with, for example, use of ice-covered regions by industry. And that, of course, also drags in, whether you want it or not, drags in the scientific community. And it's an interesting question to ask, well, what role can we play as members of academia in these various interactions? So the first thing then I want to do is just briefly review with you what we have in the way of rule sets or regulations, which my colleague Amy Lovecraft here, who's been working on this with me for a number of years, and other political scientists typically refer to as institutions or institutional regimes. And for me, as a CS researcher, my take is, hey, if I work out of the field in the Arctic, the minute I'm on a snow machine out on the sea ice, nobody's going to tell me what to do, right? I mean, or at the very least, it's going to be one of the local experts that we listen to very carefully. But other than that, you can basically design your research program as you see fit. Well, in this institutional analysis that we performed, we found that there is close to 24 different rule sets, so specific laws, local ordinances, a range of formal and informal rule sets that govern use of sea ice. And in fact, what we're seeing is that the academic research community is increasingly being impacted by these rule sets as well. I've listed here some of them. There's a whole bunch of abbreviations in there that you may or may not be familiar with. But it's interesting to, for example, keep in mind that in the U.S. Arctic, the equivalent of a county in the lower 48, the North Slope Borough, actually has ordinances on the books that govern what you can and cannot do as a research on sea ice. And of course, a lot of these ordinances are the result of the fact of increasing use of coastal ice by industry. So that's an important thing to keep in mind. And what Amy and myself and Shanna Meek have proposed here is that we can use these institutions as a guiding and prioritizing element to tell us where to make observations, how to make observations, and then how to feed these observations back into the, if you will, into societal space to ultimately and ideally inform sustainable ocean use. So as an example now, I just want to highlight this on a map here. And again, I'm not expecting you to be able to read any of this, but this is essentially Alaska's northeastern Chukchi and Beaufort Sea coast. This here shows you spatial patterns associated with any of the institutions associated with polar bears. So this includes Endangered Species Act regulations, designations of critical habitat, what have you. It also includes around some of these communities the areas where hunters are out on the ice. And again, these hunters, because polar bears are co-managed at the federal and local level, actually have a role to play in this. But it also shows you some of these in yellow here, the active oil and gas leases. It gives you the territorial waters, and it shows you some of the sea ice features such as open water or the extent of landfast ice. And what we're finding is that, in fact, in these areas, there is very high institutional density, lots of regulations pertaining to sea ice use, but these regulations are not designed with a rapidly changing sea ice cover in mind. Some of them don't even have a sea ice cover in mind per se. It's incidental to these regulations that they're now all being used to, for instance, channel the activities of industry in those various areas or guide the outcomes of different lawsuits that pertain to, say, the status of protected marine species. And so again, on the one hand, if you analyze this, you actually find that this may help you. Institutional density, the number of institutions here that govern different uses at specific locations, may actually help you in designing an effective observing network or observing system that meets one of the primary goals, as we would argue, that the role of scientific data and information can play in sustainable ocean use. And so sort of from a theoretical perspective, I've tried to sketch this out here, that on the one hand, you have stakeholders who have specific desired outcomes in mind, let's say exploitation of oil and gas resources, protection of polar bears, non-harassment of polar bears. And on the other side, you have the scientific community sitting here studying Arctic system science questions. So as an example, somebody might be looking at, well, are the changes in the sea ice cover we're seeing today reversible? Are we entering into a new sea ice regime that we're basically going to be trapped in for the next few decades or centuries? The question, of course, is can you translate some of the scientific activity into specific actionable information or information products? And in theory, you can. That's where this whole concept of the services and the uses people and or organizations derive from the Arctic system comes in. But even under those circumstances, you need what one might term information bridges or interfaces that help you turn data and observations, which are collected for a variety of reasons, into information products that directly address desired outcomes. So as an example now, we did a little case study here to see how much of this is actually implemented. And so the question was, what data sets for the time period 2011 and 2012 do we have in the U.S. Arctic ocean areas? Any type of data that's publicly accessible or not that might be of interest here. It turns out that the most reliable data source for this and the most prolific data source is the Alaska Ocean Observing System. So this here gives you a subset of the observation. So you can see there is a very dense spacing here in some of these areas. And so you could argue, hey, you know, where's the problem? I mean, we have data galore, but when you look at this in more detail, and this is work Olivia Lee, a postdoc who started work with me, did. Once you analyze the data availability, there's a number of interesting things that emerges. First of all, the first data step that we took was to look at the National Oceans Data Center, and it turns out very few, in fact, only one country is in compliance or near compliance with the requirements or the guidelines of UNCLOS's marine scientific research requirements. Very interesting question, because a lot of countries, including China, South Korea, Japan, are collecting data in this area, but they don't show up in the databases. Second point is that out of a total of 46 programs, each generating between 1 and more than 20 data sets each, roughly half of these programs actually indicate that data are not available from these programs. Now, what does non-availability mean? That's actually an interesting point that we dug into a bit more detail, and I'll show you some of that later. The others, in theory, are available, but in the end, one of the things that emerged is that at the present time, really only Arctic Observing Network projects, supported mostly by the National Science Foundation, are in compliance with making data accessible. And those are really the only projects where if you go into the AU's database, you can, one way or another, dig up the link to an actual data access site. For these others, it requires, I mean, we've asked for information on various data products. It takes quite some time to get feedback at all. For some of them, you know, we may never. So the paradox here is that even though there's a lot of data collection activities, there's very little coordination, both in data acquisition and in program design. And of course, the question is, well, what can you do about that? So here's just a brief summary. So this is what we would consider practice, and that is that currently it's mostly within the scientific community that these data are generated and used. There's very little effective data and information exchange, but there's also very little engagement of the stakeholders in helping define the problem, which is an important part of this information exchange. And of course, you have all these different entities here. A lot of the data owners currently are in the private sector because industry is funding a lot of these data acquisition programs. So how do you break through that? Well, I want to show you one example here as a little case study that sort of shows you a bit more of the details of what the issues are, but maybe point also to some interesting solutions to pursue. So these are here for mid-November, location of the lease areas in the Chukchi Sea. You might have read about this. Shell this summer and fall started exploratory drilling in this area. And the regulator, Bureau of Ocean Energy Management, requires that these activities terminate at some date prior to the onset of freeze-up. And that, of course, you know, implication is that, well, if there's an oil spill, you need to have time to clean that up, et cetera, et cetera. So there's a lot that hinges on the window of opportunity that industry has to work in this realm. Now, when you look at this in detail, so here's the ice management plan as part of the environmental impact and exploration plan. And again, you know, I don't expect you to read any of this in detail, but essentially what you have is various information sources about the date of freeze-up. When do we start to see the first ice forming on the ocean in the fall? Some of this is climatological data, some of it is operational data. That gets fed into what's essentially a proprietary analysis center that sits over with industry, but that requires the regulator to be informed, because the regulator, in this case here, this is still before the onset of formation of BSEE, so the enforcer essentially says, well, you know, once you hit that certain date, you're going to have to terminate. Now, what's interesting is, if you look at these various data records, some of them come out of academia, some of them come from the National Ice Centers, some are from other sources. They actually diverge with regards to how freeze-up evolves over time. So we looked at this. In blue here is the longest data record, last day of prudent navigation determined by the National Ice Center. You can see there's a slight increase here between the 1950s and today, 2012, this year. But at the same time, the satellite passive microwave data that the Bureau of Ocean Energy Management analyzes show a much greater delay in the onset of first ice formation. And if you involve local experts, you find yet a different picture. So it's clear, in summary, for this particular example, that there is, in fact, no consistent definition of freeze-up. That opens up, of course, for some people that's an opportunity. For some entities, for others, that's a concern. But clearly, from a scientific community perspective, this is an area where more research needs to be done to arrive at a unified, more comprehensive data set. So the interim conclusion here is that what we're looking for here is a definition and data acquisition strategies that involve the stakeholders as well as the scientific community, that also deal with the challenge of data archival, interoperability, and so forth, so that in the end you can translate this information across different uses, and you end up with a data set that is both rigorous, but at the same time also meets some of the information needs of the different stakeholders. So this is just a summary here showing the this diagram I showed you earlier, but highlighting sort of the different uses that just this information on freeze-up may have from an Arctic system science perspective, ranging between looking at ocean heat, atmosphere heat transfer, predictions of delayed freeze-up. But the one area where we see the greatest willingness to collaborate, and where arguably, and that's sort of the conclusion I would draw here with the presentation, where we might want to start pursuing some of these ideas in more detail, is with respect to safety of operations and emergency response. Well, how do you do that? So I just want to spend a few more minutes now talking specifically how you can put these information bridges in place and try to build what you might call communities of practice that involve various stakeholder experts, the scientific community, the regulators, experts from the private sector. We've done this in collaboration with the National Weather Service, the Eskimo Walrus Commission, the Co-Management Commission, NOAA, and local experts in different coastal communities in the Arctic, in the Alaskan Arctic, essentially to improve the weather forecasts and ice predictions that the Weather Service puts out by involving experts at the local scale to provide quantitative feedback or information on the accuracy of these different forecasts. And I'd encourage you to just Google CS4Walrus Outlook. You can learn more about this project. It's been an interesting experience because we found, example here, AVHR visible range satellite scene for the Bering Strait area. We've looked at various types of satellite data. This is a Japanese ALOS L-band pulsar image where we've had very detailed discussions with both the regulators, local experts, and others about safety of operations and ice conditions in these types of environments. And this project now has grown to sort of the next level where we're starting to work with, in this case, for instance, Alaska Native Tribal Health Consortium, where we're linking this information about changing ice conditions to health at the community level. Where, for instance, during freeze-up, these are observations that are ongoing this fall during the freeze-up season, where you see substantial hazards, of course, during the ice season with coastal structures threatened as well. So in conclusion, then, I think there's two points to take home from the work that we've been engaging in here. So the first one is that there is a significant pull to be had, or if you will, the carrot of this whole thing is that the changes we're seeing in the Arctic, the opportunities we have for generating new insights, new information about a rapidly changing environment and how we as people and communities can adapt to that change is substantial in the Arctic because there are no firmly set structures. People are open to collaboration, and the formation of these communities of practice is one way to improve interoperability, to arrive at common standards, best practices, and move forward in a constructive fashion. The challenge, though, is, and I would argue that at the same time you do need some type of stick, or at least the ability to point to a stick at the higher level, and that is that currently there are no support structures for prudent data co-management and data co-production. So the challenge really is that at the regulatory side or at the government side, creation of a cross-agency entity that facilitates these types of collaborations and allows communities of practice to grow seems to be something that needs to be thought about more seriously. Thanks.
Thank you, Hayo. I think in the interest of staying on a fairly tight schedule, we'll hold the questions until the end. We do have a discussion session scheduled at the end of this overall session. Here we are. You might just put this on so it's close to your mouth. Get it.
That's good. This doesn't work. Oh, okay.
So our next speaker will be Fiorenza Micheli, who will talk about climatic impacts and resilience of coastal ecosystems and fisheries.
Here's the mouse, so you have the control of this.
Okay, great. Thank you. Good afternoon, everyone. I'm going to present work that is the result of a collaboration of a lot of people, too many to list in the abstract, so I listed them in the first slide. And I want to start with the map that was generated through a global analysis that Ben Halpern and several of other people, including myself, did a few years ago, where we attempted to quantify and map the global impact of the multiple pressures that people exert on the oceans. So what we found is that most of the oceans is affected through a series of pressures, and that the hot colors there that you see on the map, the heavy impacts, correspond always with multiple pressures. So this is it's a global problem, and it's a result of a suite of different activities. In a similar global analysis that was conducted by others, these authors modeled the effects of climate change, temperature warming in particular, on fisheries catches. And so the point I want to make here is that there's impacts on the oceans that we had documented, but there's also loss of ecosystem services, and that this loss is not homogeneous. And here what you see in the map is that some communities, some nations will see a significant decline in catch, in fisheries catches, up to 50% over 50 years. Those are the red areas. And while others will see an increase in catch. So that, to me, really brought down the global problem to a local level, because the local communities will see major challenges, and challenges that they can't address directly through their actions. One, and I'll go back to this point in a minute, but one stressor that wasn't included in this analysis is the documented deoxygenation of the ocean. There's been analysis that have shown both an expansion and a shoaling of oxygen minimum zones, zones of low oxygen that naturally occur at depths of 500, 600 meters or greater that are coming closer to the surface and to the coast. There's been documentation of hypoxic and even anoxic events in open coast ecosystems, such as the California upwelling ecosystem. Analysis showed that these events had no precedent over the past 50 years at least, and were associated with mass mortality of species of commercial importance. And then in a study that we haven't published that yet, that's in preparation, we use a long-term data from the Southern California Bight, from the water quality monitoring programs, and found a very significant decline of oxygen content in coastal waters at depths as shallow as 15, 20 meters over the past 15 years or so. So this is another pressure that goes to add to others, and it's been suggested that this decrease in oxygen is linked to climate change, and this is a simple conceptual model, a cartoon, that attempts to explain how that might be, both as a result of decreased dissolution of oxygen and decreased mixing associated with temperature increase. The oxygen minimum zone is expanding, and so it's coming up closer to the continental shelf, and in upwelling areas, during intense upwelling, these low oxygen waters are advected on the shelf, bringing low oxygen but also high nutrients, and the enhanced primary production that naturally occurs during these events further contributes to deoxygenation through biological activity. So we might hypothesize that in addition to the several abiotic changes that accompany climate change as a syndrome, decreased pH, increased water temperature, change patterns in upwelling affecting productivity. We also may be seeing coastal hypoxia in open coast ecosystems as potentially a result of climate warming. So there's an additional pressure that goes to add to many, and I show through a case study why this is important and a real challenge for sustainability of coastal economies. So a big challenge that we're facing in coastal ecosystems and for coastal human communities is that the sources of these problems, the sources of impact, are often far removed. This includes climatic changes, but also many of the sources of pollution that are affecting communities. And this raises the question of what one can do at local levels to adapt or mitigate some of these impacts. So I want to, through a case study, through a place where we've been working in for over a decade now, illustrate some of the actions that can be taken at local scales and some demonstration of effectiveness of these actions, because we talk a lot about some of all of these tools, but often we're not sure how well they will work in a changing climate. So the system I'm going to talk about is Baja California in Mexico, the Pacific coast of this peninsula. This is a very productive, very diverse ecosystems due to persistent upwelling that brings up nutrient-rich waters along the coast. So it's a kelp forest community that borders a desert, essentially. So it's a very unproductive system on land, but extremely rich underwater, home to several species of mammals, sharks, tunas, and other species of great economic importance. The coast of Baja sees a whole suite of communities that are organized in cooperatives, which were granted exclusive access rights by the Mexican government in the 30s and 50s. So essentially these communities have exclusive access to a series of species, all of them benthic invertebrates like abalone, lobster, sea cucumbers, sea urchins. They're the only ones that can harvest them within those concessions that you see there highlighted on the maps, and so the only one that can reap the benefits of these activities. And they've become sort of the poster child of success for small-scale fisheries when in 2006 they were recognized by the Marine Stewardship Council with an eco-label for sustainable fishing for their lobster fishery, the first small-scale fishery to be certified in the world. So this is the success stories. Lobster catches have been stable and even increasing in recent years, and they sell the lobster for approximately $50 a kilo to Asian markets primarily, and some in the US. Another product that has really made these communities sort of thriving over the years is abalones. This is a big snail that has an incredibly high value. It's now up to $120 a kilo, and has been really sort of the fuel, the engine behind the success of these communities, but has seen major declines too, starting in the 80s and then again in the 90s through a combination of past overfishing and ENSO events that have affected this population. So in response to these declines and the concern of the coastal communities, one of the communities has voluntarily established marine reserves within their concession. So they have committed not to harvest anything within a portion of their fishing grounds for a period of 6 years. And we've been working with them and several different entities in assessing the success of this measure that they have taken at high cost, because when they forgo abalone catches in particular, there's a big loss of money that they incur, especially over a period of 6 years. So during our studies, we have found that some of the species have responded to the protection with significant increases. This includes all lobsters, sea cucumbers, but others have actually seen some pretty significant declines, and abalones are among those. In 2009, the fishermen called us because they started seeing dead animals everywhere. We went in, we documented the mass mortality event of abalone and other invertebrates as well. And this happened again in 2010. This is a long story, but I'll summarize it to say that we think that the mortality events are caused by hypoxic events, similar to those documented off the coast of Oregon that have affected these areas in 2009 and then again in 2010. That's the light blue site is at about 15 meters depth of water. It's the deepest of those three, still not very deep. And the low oxygen conditions that we documented have lasted for periods of, in some cases, 3 weeks, and at levels of 2 milligrams per liter, which is lethal to most organisms, for periods of 3 days at our sites. So this may be the manifestation locally of these more general changes that are affecting upwelling-driven ecosystems that might be particularly intense in areas of persistent upwelling there in the pink that also have a narrow continental shelf, so that you have at the same time strong advection of low oxygen waters on the shelf and then sort of a short distance to travel to get to the coast. And so the arrow indicates the location of our site, but several other communities within those pink areas have seen similar events starting in 2009. So through our studies on the reserves in particular, we documented a role that reserves may play in not protecting populations, marine population from these events, but allowing for more rapid recovery. So we did a series of recruitment studies. We put collectors like those that you see up there in the picture on the left, and here we report the abundance of abalone post-larvae, the little guys there in the picture, before and after the mass mortality event in 2009, so 2008 and 2009. And what we found is that in the reserves, recruitment is maintained, whereas there was a 4-fold reduction outside of the reserves. So this happens not because the animals don't die inside of the reserves. They're affected by these events equally in and out of the reserves. Of course, the hypoxia can easily cross the boundary of the marine reserves. But what happens is that the animals that survive have a broader size range because they're not removed by the fisheries. Abalones, like many other marine invertebrates and fishes, have a fecundity that increases exponentially with their size. And so reproductive output essentially is maintained, and recruitment is maintained, and we also documented a spillover, an advection, a migration of larvae across the edges of the reserves that goes to reseed the adjacent depleted fishing ground. So this is a story of success of marine reserves in the face of events that local communities cannot address directly. It really gives us hope that some of these local instruments, tools that have been proposed for adaptation may actually have a great potential to allow communities to respond to climatic impact or others that they can't control. So we put all of this information together in a demographic model for the abalone populations in particular to project what might happen under different scenarios depending on what are the decisions that the community take. And there I'm showing the trajectories of catches that we project without reserves, that's the 0%, and with different fractions of the coastal habitat in marine reserves in the future. So first of all, based on our assumptions and our data, without reserves, we predict the population and collapse over a period of several decades. With the current size of reserves, which is 10%, we predict potentially recovery of the fishery, but over long periods of time. So it takes at least 10, 15 years to even see the benefits of the reserves and have catches that surpass what you would get without. And then as you increase the extent of protection, we predict greater benefits. Following the mass mortality events and our presentation of the studies, several of the communities have committed to marine reserves, and the Isla Natividad community that we work with has renewed their commitment for the next 6 years. But of course, the concerns are major because we don't know what is going to happen. our models account for current natural mortality. If the frequency or the extent of these events increases, those projections may be too optimistic. And also it's going to take a long time for the people to reap the benefits of the huge investments that they're now making into conservation. So there are other ongoing activities that are carried over by an NGO in Mexico, Comunidad en Biodiversidad, that are our partners on this project. And one of the initiatives is to expand the concession rights that the communities in coastal areas currently have to other species. Basically, the problem is that right now the exclusive access privileges only regard a few species, and so there's an incentive to invest in the conservation and good management of those, but at the same time there's overfishing of a suite of other species that are open access fisheries. And so the idea is to expand concession rights to the whole ecosystem so that the local communities that will invest in these adaptation strategies in conservation may be able to then reap the benefits of the ecosystem and ecosystem services as a whole through a portfolio of different fisheries that currently have very low value and are open access, and through other activities like recreational activities like ecotourism and aquaculture and other things. So this has gone all the way up. It lacks presidential signature. Everything got stalled because of the election in Mexico, and right now it's not approved, but it went up fairly high in the legislation in Mexico, and we may hopefully see in a few years this new tool that the communities may have. We're also attempting to increase the value of some of these alternative species that are doing so well under the current climatic conditions. This includes several finfish species. And we are working with partners in marketing these species in the US for a higher price. Right now, some of these species are sold for $1 a kilo in local markets, whereas if you go to any seafood market here in California, you will see much higher prices for halibut, yellowtail, and all of the species that they harvest there. So the idea is to create these incentives also through financial mechanisms, such as the certification like here or payment for ecosystem services, and so to help the communities take some of this investment in conservation back, and so to carry them over through those long periods of time that will take for marine reserves to actually work. So the challenges are daunting and global, but basically my message, I think, is a very simple one. There are a lot of things that can be done locally that have proven fairly successful and that can be tried in different settings, not just in Baja. The reduction of cumulative impacts through marine reserves that have been suggested, but also highly criticized, because one of the many responses is, well, what about climatic impacts? No, reserves will not work under these current climatic pressures, where there's some evidence that they might, in fact, play a role. And then at the same time, use a suite of tools that we have in hand, including area-based rights and some of these financial mechanisms like payment for ecosystem services and other ways to create incentives for adaptation at the local level. Okay. Well, actually, I have finished, so I have 3 minutes for questions. Okay, thank you.
Any questions out there? Questions up here? Do you suggest some other system that immediately might come to mind that you could apply this ecosystem approach to?
See, it has a long history in coral reef ecosystems. There's, in terms of systems that lend themselves to this kind of approach, it's almost all coastal ecosystems. What is often an obstacle is the human conditions. The system where we work lends itself to area-based management because of the concession systems, because they have by law exclusive access. So often the open access, the lack of clear property rights, in a sense, in the ocean is a major impediment. So in some tropical communities, in communities in Chile, for example, there's other example, because there is this system legally and in the societies, then you can implement this tool. So the first obstacle, in a sense, is to apply more broadly these access privileges to marine ecosystem, like catch shares or area-based management, and then not to creating the incentive and financial conditions to sort of implement some of these measures.
Did it spark any more? How, just very briefly, the Gulf of Mexico is one of our worst problems. And forgetting about the oil spill, an awful lot of the pollution comes because of farm waste and so forth coming down from the whole interior of the country. This is a source very far removed from the problem area. And in 46 seconds or less, can you tell me how you'd approach that?
In general, no, I focused on hypoxia and temperature changes as a stressor, but in principle, any stressor could be addressed at a local scale by decreasing other pressures. So basically the idea is to reduce the cumulative impact and maintain systems that can respond to this perturbation. So it wouldn't address the impact of the oil spill per se, but may create the conditions for faster recovery. So addressing cumulative impacts is something that has been suggested. There are tools like marine reserves and others, and I think broader application of this tool to make some demonstration projects, some sort of examples of how it might work are really important in systems like the Gulf of Mexico in particular, I think.
Okay. Thank you.
Thank you very much.
Go on to the next talk now.
Okay, so we're going to move on to policy, and our next speaker is Jerry Miller, who will talk to us about U.S. national ocean policy, science for sustaining ocean resources.
Thank you very much, and I think it's great that we're here talking about sustainability of ocean resources and sustainability sciences that will allow our policy folks and management folks to get on with that sort of management. I want to start first with a slide that I got from Frank Princiotta a couple of years ago. This is to describe the big picture, the big sustainability picture, and then I'll delve into some elements of ocean sustainability. We as humans need a lot of different things. Food, shelter, we like to have good transportation, lots of things that make our lives easy to live. But the demand that we place on the environment is growing. Estimates are individual demand grows at about 3% per year, especially as economies around the world develop. Population also increases. This means that total demand that we're placing on the Earth system grows dramatically year after year, decade after decade. We use various technologies and practices to extract those things that we need from the resources that we have. This involves industrial production, agriculture, energy production, etc. Those things draw on the environment. Fossil fuels, water, various minerals and materials, and they produce things like CO2, which have a feedback on our environment. Those processes and practices, in turn, have impacts of their own on oceans, forests, on our health, on our air quality. Of course, we use up resources, we use up water. Not all of it gets recycled in a usable way. And then there's climate change that sort of changes the baseline on which a great many of our processes and practices were initially developed. This all together creates challenges to the long-term sustainability of this grand system upon which we so intimately depend. As we look forward, we can think about new technologies, new practices that will mitigate our impacts on that system. I think there are opportunities for research and development there. There are also changes that we can make in the social and cultural realm, and this requires scientific developments as well to help us guide it over time. I think the ocean community plays a big role in this picture. Just on the climate change question, in my view, climate change is about 98% in the ocean. We live on land and we breathe the atmosphere, but the ocean is a key part of climate. And of course, as we look at this system and focus in more detail on the ocean pieces, we see that our human and ecosystem health is a function of what we do to the ocean. We'll hear more about that in the next presentation, I think. Changes in the ocean environment, warming in particular, will change ecosystem structure and function, and obvious things like the migration of species to latitudes at which they did not occur previously. Coastal communities, we saw in the first presentation in this section, impacts on coastal communities. We just heard about biodiversity issues, fishing and smart ways to manage extractive fishing approaches from our coastal areas. And then, as I said earlier, exacerbating all of these challenges is the increased number of humans and the increased human demand on the system. All of this drives the need for basic and applied ocean research. We use the ocean in so many different ways for so many things. Our society depends on it, economies depend on it. We know about environmental concerns. Our national security depends on it. But at the beginning of the Obama administration, several of us realized that we didn't really have a coherent policy, a stated policy here in the U.S. for how we approach the ocean and the benefits that it provides to society. Other countries do. We were a little behind the game. To make a long story short, we worked with a lot of brilliant people, including a great many people who are at this meeting, some of whom are in this room, to help us formulate a national ocean policy that was drafted, edited, redrafted, commented upon by the public, and eventually signed out as an executive order 2 years ago. Now we're in the stage of figuring out what we're going to do about the objectives that were stated in that policy. There are 9 of them. There are 4 that are focused on how we as a nation go about doing our business, and 5 of them we call areas of special focus. I want to talk primarily about these 5, and after I've done that, I'll circle back to ecosystem-based management and also means for improving our decision-making processes and better understanding the ocean itself. So first, resilience and adaptation to climate change and ocean acidification. Climate change and acidification, of course, are 2 separate manifestations of having too much CO2 in the environment. They separately and together create stressors on the environment along the lines of what we saw in the last presentation. And of course, one can debate recent events, but I think there's an argument that large storms, unusual storms of the sort that we saw on the east coast of the U.S. Recently, might be a manifestation of this change, and therefore a fine example of the need for developing resilient communities and learning how to adapt to the coming changes. Ecosystem protection and restoration, whether we're talking about large bays and estuaries like the two pictured here, or smaller systems in other areas, or even the open ocean, we really need to have our community thinking about the science that lies behind integrated ecosystem protection and restoration. Water quality and sustainable practices on land is the third focus area, and this gets to Robin's question from a couple of moments ago. What we do inland, whether it's in the U.S. or elsewhere, ultimately has an impact on our oceans. Some of the impacts are localized, some are quite widespread. We have hypoxic zones not only in the northern Gulf of Mexico, but in other places around the U.S. coastline and far-flung around the world, driven by what would otherwise be perfectly reasonable practices on land. We're beginning to see early scientific results that tell us that smart practices by farmers, that is, smart in the sense of making them more productive and more cost-effective, are also good for the coastal ocean. So we need to pursue that sort of science. The only geographic area that is specifically called out in the U.S. National Ocean Policy is the Arctic. And that's simply because we believe conditions are changing so rapidly there. We know climate is changing. We know that coastal communities in Alaska are facing significant challenges. We've seen impacts on certain species, both on land and in the water. And we know that commerce is coming to the Arctic, whether it's shipping, whether it's oil and gas activities, or other activities that will come once the Arctic sea ice has sufficiently retreated that other activities can take place. So we need to get ahead of the curve for Arctic ocean sciences. Underpinning all of these is an objective focused on better observations, mapping, and the infrastructure to support the collection of data and the creation of information that's necessary for better management of ocean resources. I won't go into all of the details here, but this certainly ranges from satellite systems for which we in the U.S. and we as a community globally have some significant challenges, to in situ systems that are newly developed and coming online that will give us innovative ways for measuring things beneath the sea surface. So we need to be hitting on all cylinders as we bring our observing wherewithal to bear on the focus areas that I've already mentioned. All of these then collectively feed into my view of ecosystem-based management. Previously, we tended to manage on a species-by-species basis. If a particular species was overfished, then we had to do something about it. If a species became threatened, we had to do something about it. But I think we now see that we need to look at the entire ecosystem, again, in the way that the previous speaker alluded to, and that ecosystem includes us humans. I'll remind you of the first slide that I walked through where we humans are an intimate part of this system because we depend on it for so much of our lives and livelihoods. And lastly, let me talk about the objective that focuses specifically on improving our understanding of the ocean. This is the home in our policy for pure exploratory research, basic research that might not necessarily be resource-driven at this stage or mission-driven at this stage. And it also focuses on education. If you were in the midday lecture given by Ara Flatow, I think you saw a lot of good examples for how we can do a better job as a community educating the public. And from where I sit at the White House, there's definitely a need for educating our folks on Capitol Hill and, in fact, in governments all around the world with respect to the importance of what the oceans do for society and what we as society need to know and appreciate about the oceans. So we have these 9 objectives. I hope that a large fraction of you saw earlier this year a draft implementation plan which we put out for public comment. It identifies specific, measurable, short, mid, and long-term actions to help us meet those 9 policy objectives. The early phases, of course, build on things that are already ongoing now. It identifies federal agencies that are responsible for each milestone, under each action, under each objective. And it sets deadlines by which agencies are supposed to have met those milestones. And it attempts to identify gaps and needs in science and technology, although I would admit to you now that I think the current document falls short a bit in that respect. There's a lot of motivation there, but specificity about the science and technology that's needed, I think, is a bit short. This document's been in process for quite some time. It's still under review. I hope that we have it wrapped up and ready to deliver to the scientific community and to the public early on next year. And I would, again, thank everybody in the room here who provided input to both the creation of the policy initially and to the outlining of these implementation plans. Now, I could stop my presentation here, but I want to answer the question that I always get. I'm the White House guy. People always ask, what are the budgets going to look like to carry on this work? My crystal ball is not clear enough to tell you what Congress is going to do, especially under the current budgetary climate. Everybody has heard about the fiscal cliff, sequestration, the task that lies before Congress and the administration. I don't know where that's headed. We hope that we have a logical and productive conclusion for it. I would also mention that the U.S., of course, is not the only nation that has budgetary problems these days. Our European partners are faced with significant challenges. I was just talking to a colleague from Spain. They are heavily impacted by what their government has been forced to do with respect to funding for science and technology. We live in challenging budget times. But I want to tell you, so I have no crystal ball to look into here, but I want to tell you what the current climate is. This is what the President's proposed fiscal year 13 budget looked like. And I'll ask you to focus on the dark blue on the right-hand side and the light blue that's just above it. That is the discretionary spending portions of the budget. And then further, if you'll focus on those 2 little slivers that are called out from the pie diagram here, that's where the entire U.S. research and development budget resides. It's all in the discretionary part of the budget. Some of it's defense-related, some of it's non-defense, but it's those very narrow slices. And let me emphasize again, that is all the entire federal R&D budget. Ocean sciences fits somewhere inside of those 2 little slivers. So that's the environment we work in. And here's what the official budget projection was back in January or February of this year. Yeah. And I'll draw your attention to the bottom of this chart. The color coding is the same. The dark blue and the light blue, the two elements on the bottom, what's happening to them? They're projected to get smaller. So our R&D world resides in those two thin slivers, and the home for those two thin slivers is getting smaller over time. It's not a pretty budget picture. It's not an encouraging one. But I will tell you that the President is serious about investments in R&D, even given these trends, which are depicted here from starting in 2011. In 11, 12, and in his budget request for 13, we actually grew the R&D budget. Despite the trends that you see here, R&D is up. Not a lot, just a few percent, but it is in fact growing. So we're bucking the trend of the overall budget, and I'm hopeful that we can continue to have that positive deviation for the R&D budget as we go forward. And I'll stop with that. Thank you.
Oops. Thank you, Jerry. We have time for one question. Sure.
Yes, Eric.
Thanks, Jerry. One of the companion documents to the National Ocean Policy Implementation Plan is the Ocean Research Priorities Plan. Whatever became of that?
Yes, thank you for asking that question. Yes, Eric is asking about the status of the update of the Ocean Research Priorities Plan. This is a document that was produced back in January of 2007. The first time that the U.S. ocean sciences community had kind of a community-wide national priorities plan to help shape ocean research. We saw a need to update that plan for various reasons. Things change. We know now about ocean acidification, for instance. That wasn't really addressed in the first incarnation of that plan. A long time ago now, it seems, we set about developing an update for it. It's been in the works a long time, far too long in my opinion. But we did want to make sure that before it's finalized and released, that it was at least congruent with the objectives of the U.S. ocean policy. We would not want to be saying one thing to the community with an ocean research priorities plan and something different or opposed with the national policy. So there's been a kind of a reconciliation step that was necessary, and I'm hopeful that it and the ocean policy implementation plan can be rolled out early next year.
Okay, thank you.
My pleasure.
I'd like to invite our next speaker to the podium, Paul Sandifer. And Paul's going to tell us a little bit about oceans and human health, linking ocean, organism, and human health for sustainable management of coastal ecosystems.
Thank you. And now I get to talk about a tiny, tiny, tiny sliver of those tiny slivers that Jerry just mentioned in the budget. If we can get this back up here. Scientists have known for a long time that the health of coastal communities depends on healthy ecosystems. But what we've just been learning in the last couple of decades is how closely the health of coastal ecosystems and in human communities then are affected by degraded environments, resulting in things that, like Jerry mentioned in one of his slides, increasing amounts of harmful algal blooms and pathogens, as we heard in a previous talk, increasing hypoxia and a variety of other things. So let's see if I can make this go back up, if I can. Oh, all I'm doing is going forward. So there we go. So I want to talk a little bit about oceans and human health. It's a relatively new meta-discipline. I call it a meta-discipline because it combines elements of a variety of disciplines. This is the one place in science these days that we really bring together oceanographers, marine ecologists, marine biologists of all kinds, fisheries folks and such, with representation from the health sciences, including the public health, which is different from the medical schools directly. So medical, biomedical, public health, and marine sciences. Focus is principally on water and foodborne diseases coming out of the oceans and coastal waters, including the Great Lakes, but also on natural products like new pharmaceuticals and other health benefits, including healthful seafood. And it integrates a lot of information across multiple sectors, developing decision support tools. And there have been named ocean and human health programs now in at least 3 agencies and a host of related programs. The 3 agencies are the National Science Foundation, National Institutes of Environmental Health Sciences, and NOAA. And I'm going to just pull together a sort of an amalgam of all of these things. I want to just give you a quick report on the kinds of things that these programs, these OHH programs, are contributing to society, and particularly into the scientific community that helps us develop more sustainable coastal management programs. The first of these is this national focus on human health as being part of the ocean research enterprise. And we saw this beginning with the NRC report in 1999, Monsoons to Microbes, that literally led to the development of named theme programs, Oceans and Human Health. We saw then the passage of the Oceans and Human Health Act of 2004. We saw this reflected in the Ocean Commission report of 2004. We saw ocean health themes reflected in the Bush administration's Ocean Health Plan. And we really saw it coming to existence in the ORPP that Jerry just mentioned, the first version of the Ocean Research Priorities Plan in 2007, and then an integrated science plan that came out of our interagency working group on oceans and human health, basically human health, hypoxia, and HABs. And finally, it shows up in many, many ways in President Obama's executive order, creating the first ever national ocean policy in this country that Jerry already alluded to. And we've seen that it developed major sustained connections and collaborations. We've had 7 centers of excellence in oceans and human health named within agencies and within academic environment and academic institutions in this country. And those have developed, even though each one was separately designated, have developed into a network of very closely related laboratories. We've seen this enhanced interagency coordination beginning with things like the foundation of an interagency working group on harmful algal blooms, hypoxia, and human health that I just mentioned. Lots of interagency activities, but leading much beyond that to the community then developing its first ever textbook for advanced level undergraduate and graduate education programs in oceans and human health. We've also seen much increased linkages, understanding of linkages between marine animal health and human health. And I put this slide in here, and some of you may have heard a previous talk I gave today. I've used a number of these health things to bring home the point. This is to illustrate the ubiquitous connections between people and marine organisms, in this case marine mammals, and the potential for transfer of zoonotic pathogens from marine wildlife to humans. 60% of infectious diseases of humans comes from zoonoses, that is from animals, and 72% of those things come from wildlife. So we have plenty of potential for all kinds of things. Like this case, it's a tropical fungal disease now moving northward, found commonly in dolphins, also found in people, and exchange between the two. And another case here, let me back up one second. Another fungal disease, not illustrated on this particular slide, but Cryptococcus gattai was first discovered in the United States. It's a tropical disease, didn't show up in the U.S. at all until 1999, and all of a sudden it showed up in the Pacific Northwest. And the first case in the U.S. was in a porpoise. It then became epidemic in domestic animals and in humans in Canada, Washington, and Oregon. Probably not transmitted through the marine environment, but the potential is there. And one of the other cases that I mentioned earlier today is this one, where we saw an initially unexplained mortality event for New England harbor seals last year. 162 animals died of pneumonia that was associated with a strain of avian influenza that had been circulating in North American waterfowl since about 2002. And the importance here is that this particular strain now in the harbor seals had demonstrated the acquisition of mutations that allowed it to be transmitted and to be especially virulent in mammalian hosts. We've seen the development of a new interdisciplinary community of practice. I won't belabor this, but I will say that we now have traineeships offered in this field. We've trained more than 35 new PhDs and doctoral students, postdocs, I mean, more than half of whom have already gone into academic, governmental, and international posts working in this area. And we've already had 3 and are heading for number 4 of Gordon Research Conferences and Gordon and graduate research seminars, illustrating that this theme, this thematic area, this metadiscipline has been adopted by the scientific community at large and is becoming a mature area of development. We've seen also the enhanced ability of scientists to bring together ocean scientists and health scientists to work together to respond to catastrophic events like Hurricane Katrina and Rita on the Gulf Coast and the Deepwater Horizon oil spill and a variety of other things. This is being followed now by an NIEHS study, a 10-year longitudinal study that has already enrolled tens of thousands of responders and oil field workers to look at the long-term human health and well-being impacts of that Deepwater Horizon spill. This is the largest ever such study undertaken. And we see a lot, see if I can get it, of new knowledge about factors affecting occurrence and impacts of ocean health threats, including the climate change issues, and as well as development of new technologies, new sensors, new observing capacities, new applications of genomic and omic technologies in general to understanding and predicting disease processes. I'll note the first ever human health perspective on climate change, that's the research agenda produced by an interagency group. It came out as a result of discussions amongst these oceans and human health researchers in a variety of agencies and academic institutions. And we've seen new emphasis in an old area of investigation, that is the identification of bioactive molecules from the marine environment and their potential exploitation for new pharmaceuticals. Most importantly here, we see programs like this International Cooperative Biodiversity Group's work led by NIH, but with a number of agency participants that couples that biodiscovery work with conservation work, leading in some cases to the development of new marine protected areas in a variety of areas around the world. And we see a huge outpouring of new scientific findings from all kinds of disciplines. And this information is rapidly being picked up by the natural resource management communities, but also by beach managers, by public health officials, and others. And we've seen the impacts of communication. The public has a lot of interest in this, so there's been a lot of effort put into putting this kind of information into Ocean Today kiosk at the Smithsonian, to news media of all kinds, and of course to many scientific presentations. And finally, this effort of trying to develop health early warning systems or forecasting ecological events well in advance of occurrence so you can plan for them the same way we plan for when we can for extreme weather events. And this is one of the areas, this is where I want to end up this presentation today and tell you where we in NOAA are going. The next steps with the oceans and human health is to develop an emphasis or a roadmap for ecological forecast, putting all of the pieces we have together. We do a variety of developmental work in ecological forecasting, from hypoxia and harmful algal blooms to jellyfish and brown shrimp and Lord knows how many other things, but we do not have a consistent, coordinated effort like we do for weather events. So this is the objective of this effort. We've chosen 3 particular kinds of events to deal with. These are the most mature in terms of their progression from research to operational status, harmful algal blooms being the best of these, the furthest along. We have operational systems in the Gulf of Mexico and close to operational in a couple of other places in the country. We're aiming to develop this as a consistent national program, but with regional specificity for all three of these areas. Harmful algal blooms would be the first out of the box. And the idea here is to build upon what NOAA has done for so many years with weather and climate and be able to come down, to forecast, beginning with an event outlook, coming to finer and finer predictions, and dealing with the event itself. Right now, most of our effort is on the lower end of this curve, where we are trying to get a little better at actually knowing what the event is likely to be, where it is going to be, what its magnitude is going to be, and duration. But as we have the opportunity to move further and further back out that curve, we have the opportunity that the folks in the hurricane business do of being able to provide an outlook that says this may be a bad year for harmful algal blooms in an area or whatever, and that we can begin early preparation, begin planning responses long before an event, and hopefully take that recovery line that you see here, a very, very long one, and shorten both the magnitude of the impact of the event and the recovery period, because we were able to get ahead of the curve. So with that, I'll stop and be happy to answer any questions. I did want to end with the same kind of communication that Jerry was talking about, and that is from President Obama's ocean policy, speaking to the intrinsic linkage of the environmental sustainability, human health and well-being, and national prosperity through the oceans. Thank you.
Thank you. Any questions from down there for Paul? Sure. Could you restate the question?
I think the question is what kinds of technologies we'll be using to forecast pathogens. There are several areas we're working, mostly with naturally occurring bacteria, Vibrios. Parahemolyticus, Vibrio vulnificus causes a number of diseases in humans. Also with sewage-mediated pathogens. A couple of approaches. One is correlating the presence and concentrations of the pathogens with environmental factors, and then using the environmental factors as a proxy to predict likely distribution. The more robust way is to develop those correlations and then do a lot of sampling to confirm the presence, but being able to do that sampling based on where you think the hot spots are likely to be, and then confirm it. We have experimental models. We're working with University of Maryland and a variety of other partners right now that I don't have time to show you, but clearly demonstrate the capacity to do this in one or two locations. We have similar kinds of models for sewage-mediated pollution on beaches in the Great Lakes, but again, one or two locations. The trick is going to mature those models, get them working on the same fundamental circulation and physical model basis, and be able to produce these kinds of results consistently nationwide. Thank you.
Thank you.
Okay, so now we're going to move on to the world of modeling, which is a useful tool for ocean sustainability. Our next speaker is Steve Lorenz, and Steve will be talking about sustainable management of coastal environments through coupled terrestrial coastal ocean models.
Here, have a mouse. And you can either talk into this or you can put this to your lapel.
I guess I'll use the microphone here. It's probably just as easy. All right. Well, thank you all for your attention. And we've heard from previous speakers the challenges of sustainably managing our coastal environments. And what I want to talk about today is one approach that our group has been developing involving coupling terrestrial and coastal ocean models in a way to aid in both understanding the system, but ultimately, hopefully, in supporting management and improving decision-making related to that. So I just want to acknowledge this is a project that's funded largely through NASA Interdisciplinary Research and Earth Sciences and the NASA Carbon Monitoring System programs, although it's a project that's been in development for a long time and has had funding from a variety of other sources, National Science Foundation, NOAA, EPA, and USGS. So just an overview of the talk, I want to first just give a little bit of background on some of the issues related to coastal sustainability and management in the Gulf of Mexico, and then talk a little bit more about the project, the NASA IDS project, using the Gulf of Mexico as a case study to illustrate this approach, which, and again, this is one example of an approach but I think it illustrates a broader concept of how to look at management in an integrated fashion rather than just focusing on individual systems. And again, we've also heard from some of the other speakers in this session where they're dealing with similar challenges, and so this is maybe one perspective that we offer for the Gulf of Mexico. So then in our approach, I'll discuss characteristics of the models. We have two models, a dynamic land ecosystem model and the coastal ocean biogeochemical model, and then the integration of those two models, briefly talking about that as well. My mouse is moving on its own here, so sorry about that. And then just go into results and what are the next steps, and ultimately then, which is really still remains to be done, is the future applications of these models and the output from the models to sustainable coastal management. So the Gulf of Mexico is an area that's critically important to the nation's economy and quality of life. The 5 states of the Gulf Coast region had a combined gross domestic product of roughly $2.4 trillion in 2009, or about 17% of the nation's GDP. And there are rich economies in areas of commercial and recreational fisheries, oil and gas, ports and shipping, and tourism. Average yearly commercial landings for fisheries in the Gulf of Mexico for 2007 to 2009 was 1.4 billion pounds, valued at about $660 million, and that was equivalent to 16% of U.S. landings. Recreational fishing accounted for about 44% of U.S. marine recreational fish catch, and tourism and recreation industries account for 8% of the jobs in the Gulf Coast region, equivalent to about $29 billion in wages earned. And the population of the Gulf Coast region has increased at a rate more than double the average for the rest of the U.S. So I think this audience doesn't need to be convinced that healthy coastal ecosystems are critical to the sustainability of our coastal environments, our coastal communities, living resources, and quality of life. And there are a variety of factors, many of which we've heard about today, that threaten these systems. For this talk, I'm going to focus just on the first 4 listed here: nutrient pollution, hypoxia, ocean acidification, and another topic, carbon management, which, again, the coastal environments play a potentially important role in ultimately our ability to monitor and manage carbon in the atmosphere and in other reservoirs. So the project, the NASA IDS project, involves a coupling of terrestrial and ocean models. And the idea behind this is that we have changing climate and land use practices that can dramatically alter hydrologic and biogeochemical processes in terrestrial environments. These changes ultimately will influence the delivery of carbon, nutrients, and water into rivers, estuaries, and coastal ocean waters. And so our team is using the Mississippi River watershed in the northern Gulf of Mexico as a case study to illustrate linkages between these systems, and then use a modeling system to try to ultimately better understand those linkages as well as project into the future long term in order to support ideas or approaches to how to anticipate changes. So this is a diagram of land cover in the Mississippi Atchafalaya Basin, and the drainage basin for this river system covers about 41% of the conterminous United States. The Mississippi River is among the 10 largest rivers in the world with respect to water and sediment, and it's the largest in the North American continent. There's a very well-known or well-recognized understanding that there's been an increase in nitrogen and other nutrients from the river system, the export from the river system into the coastal Gulf of Mexico, and that has been implicated in the frequent occurrence of hypoxia off the Louisiana coast, or otherwise known as the dead zone. Again, we've heard from other speakers about the concerns related to hypoxia and the potential increase that may occur in the face of changing climate. And hypoxia also threatens living resources, so has certainly a concern, or is a cause for concern. In addition to hypoxia, there's also ocean acidification, and recent work by Wei-Jin Cai and his colleagues project an acceleration in ocean acidification in bottom waters as a result of the combination of increased atmospheric carbon dioxide coupled with respiration-enhanced carbon dioxide. The combined stresses push the buffering system of the carbon system, or the buffering capacity of the carbon system, to an area where it's more susceptible to change and may accelerate the negative consequences of this. And then lastly, just very quickly mentioning carbon management, the coastal environments represent a large uncertainty in our efforts now to constrain carbon budgets on continental scales. And these ultimately are sensitive to changes in sea level rise and human activity. So it's important then that we seek to reduce uncertainties in carbon fluxes in coastal environments in an effort to improve our ability to manage carbon. So now, referring to the project that we're involved with, basically this involves two modeling systems, the dynamic land ecosystem model, which has several modules within it, including soil, plant physiology, water, and so on, a biophysical module. And then, in addition, the ocean model here, which has a physical component as well as a biogeochemical component embedded within that. Together, these then are coupled in a fashion where the output from the terrestrial model feeds into this coastal ocean model and ultimately drives changes that can occur in the coastal environment. And this allows us then to start to look at scenarios on land related to climate and land use and how that may influence the export of materials to the coastal ocean and ultimately the conditions therein. And I'm going to just jump over these slides. I can certainly discuss these with others in more detail. But what I wanted to move on to was the model integration approach. And that is the terrestrial ecosystem model then provides outputs of freshwater discharge, dissolved inorganic carbon, dissolved organic carbon, particulate organic carbon, dissolved organic nitrogen, inorganic nitrogen, and particulate organic nitrogen. And that feeds then into this biophysical ocean model, or otherwise known as the South Atlantic Bight Gulf of Mexico model. So now I'm going to jump to work that we're involved with in sort of implementing the models. And one of the major efforts associated with this project has been the assembly of data sets which are required to run these models. So this just shows an example of cropland change in the Mississippi Atchafalaya River Basin from 1901 to 2008 by Han Chin Tian at Auburn University and his team. And you can see a dramatic increase in the amount of cropland cover. But in addition, there's also quite a large amount of abandonment of cropland in some areas. Other data sets that this group has been involved in compiling include historical and projected climate land use, disturbance, fertilizer application, and then population data. And there's a poster on Thursday if anyone is interested in more information on this. There's also a large amount of ship-based observations that have been acquired in the Gulf of Mexico from cruises that have been, taken place over the past decade. And this provides a rich data set of physics and biogeochemistry in the northern Gulf of Mexico region. So now moving on to model refinement and validation, this just shows examples of the two models being compared to observations. And we see in the top two panels river discharge and dissolved inorganic carbon. The river discharge is basically from the 1960s to the present, and you can see pretty good agreement between the model and the observed data. And similarly for the dissolved inorganic carbon from the 1950s up to the present. The model is able to simulate these outputs quite well. The biogeochemical model, then, here we show a map of partial pressure of carbon dioxide in surface waters, and in addition, then comparing that to observations of total inorganic carbon, and good agreement there as well. And then lastly, simulations of hypoxia by Katja Fennel and her group, showing a comparison to observations for a variety of different respiration scenarios. And again, they're able to reproduce the observations reasonably well. The black dots are the observed hypoxia here. So next steps then are to develop both hindcasts and forecasts. And that will be done by looking at the sensitivity to different drivers, including climate, land cover, land management, and other factors. And then using different climate scenarios, in this case a high emission and low emission scenario, to project into the future as to how climate changes can ultimately influence this system. This just shows an example of temperature in the top and precipitation in the bottom for two different emission scenarios, a high and low emission scenario. And those data then are fed into this ecosystem model. And the output from that then will be used to drive the coastal ocean model. And so this really is my conclusion slide, and kind of where do we go from here? And I realize there are a lot of steps that still have to occur for this ultimately to be a useful management tool. But I think it illustrates a concept that we have to start to look at systems in a holistic fashion. We've heard about ecosystem-based management, and I think this reflects sort of a larger perspective involving both the terrestrial and the ocean environments, because actions that are related to management in land systems ultimately have implications for our coastal environments as well, and even the open ocean. So thank you very much.
In the interest of staying on schedule, I think we'll hold questions until after the last talk. Go ahead. I'll get it set up here.
Okay, so for the final talk of the session, we'll hear from Rainer Lohmann. And, Rainer will be telling us about the pollution of oceans and Great Lakes by persistent organic pollutants. Sorry.
Well, thank you very much to the organizers for inviting me, and thank you for staying just before coffee break. So I thought I'll talk about the persistent organic pollutants, which are part of sustainable oceans. And the first thing I want to point out, so why would you make a link to the oceans for these pollutants? So the worst offenders like DDT, PCBs, and some pesticides and dioxins were officially banned or reduced in emissions over 40 years ago. So are they still present? Is there still a reason to worry? Are there any new compounds we should be looking at? And similarly, because the oceans are difficult to reach, can we make use of the Great Lakes as kind of small tests to see what will happen to the oceans with respect to these pollutants? And then lastly, if there are any chances to become more sustainable, what would those be? And certainly the engineers would say the solution to pollution is dilution, but in the case of the ocean, that gets difficult to dilute them even more. So I just want to point out that this kind of fits into the idea by Rockstrom that there are global boundaries, and several of those are well known, like the climate change or acidification. There are two slivers that Rockstrom and colleagues couldn't quite address at the time, and one of those was the chemical pollution. So the question is, how do we address the fact that every human being, every living organism is affected by a low level of pollution due to metals, mercury, inorganic pollutants? Is there a threat? Is that going to cause a problem? And the answer, we don't know, but oceans are certainly part of this question. Maybe as a background, we should probably accept that ever since humans started living, we have been using the coast and the oceans as dumping grounds for effluents, and for a long time with low numbers of people around, that probably worked out quite well. But now the cumulative impact of nutrients, pathogens, and all kinds of toxics makes it more difficult. And among the topics, we certainly have the bioaccumulating organics, which I'll talk about. We have mercury, we have metals, we have nanoparticles, excuse the scale here, and then all kinds of other human-based impacts. So that's all part of the conundrum plus atmospheric impacts. So I thought I'll start with the DDTs, which we probably all remember, affected the reproduction of the bald eagles in the Great Lakes. And that was linked to the aquatic food chain. So there was a clear link between the banning of this compound and the aquatic food chain. If we look at PCBs, we have a similar story as again from the Great Lakes, where we realized that mothers that ate a lot of fish from the Great Lakes accumulated a lot of PCBs, which led to IQ underdevelopment in their children. So again, the aquatic food chain was very instrumental in highlighting the problems. And then the last example is from the Arctic, where we know that some of the polar bears have accumulated sufficient number of pollutants that their reproductive organs are a little malformed, so they're not quite sure if they're male or female all the time. So we have problems that are at times linked to these organics, and they're often linked to the marine or aquatic food chain. So with that in mind, several countries outlawed the worst offenders early on, and this global convention came into place 2004, the Stockholm Convention. It outlawed some of the dirty dozens for the worst offenders, all aromatic, mostly chlorinated compounds. And more recently, the convention actually added newer compounds that included flame retardants and some non-stained perfluorinated compounds, the Teflon-like materials. So the list is slowly growing, and the question is, are the oceans better off or worse off? Well, let's have a look. So I want to first look at one of those few data we have from actually the ocean. This is an Endeavour transect from Namibia back to Rhode Island, which was in 2009, and I highlighted some of the ocean currents, and part of our interest was to see what kind of pollutants we can detect, and do these currents play any role in their dispersal. So this is a summary of the concentrations. On the right hand, you have Africa, going all the way back to the US East Coast, and you see concentrations of different PCBs and pesticides, and by and large you see they're present everywhere. You see some spikes, and the bottom part you see salinity in blue and temperature. And as we crossed the currents, we noticed when we hit the Benguela current, concentration of the pollutants seemed to decrease, suggesting there was some dilution from clean water. As we moved further up, we saw the South Equatorial current, slight temperature increase, concentration went up a little bit. The Amazon plume, obviously a huge freshwater input, concentrations went basically up, but not by very much. We happened to come across a warm eddy from the Gulf Stream that was a hotspot of all kinds of pollutants. And lastly, of course, the Gulf Stream and the East Coast are much higher. So what we see is, first of all, the currents distribute these compounds, and we still have the ongoing emission from land that causes some problems. The atmospheric picture is a little easier because we basically don't have defined currents for a long time, so we just see a southern hemisphere that's fairly clean. Once we cross the ITZZ, so we're in the northern hemisphere here, concentrations are much higher, much spikier, due to if the air was coming straight from a continental region or not. The main point is, of course, now putting these two together and figuring out, are the oceans still taking up pollutants or are they releasing them? And the graph is such that A value of 0 here means at equilibrium. Anything above 0 means volatilization, and below is deposition. And basically across most of the tropic Atlantic, what we see is that the ocean is releasing these PCBs and pesticides back to the atmosphere. And in a way, that is actually a success story, because it means the policies had an effect. We reduced emissions over land, so the oceans took things up for a while, and now they're returning them, so we get them back. But in a way, that's a good sign. And I guess we wish in some other scenarios we had similar stories to tell. So those are the compounds that were targeted by national and international conventions. I will show the same results here for PAHs. So these are not regulated. They're just polycyclic aromatic hydrocarbons. They don't bioaccumulate as much, but they are mutagenic, so they're not nice either. But the bottom line is that most of these are depositing. It's probably due to the fact that they are released on land by traffic, industry, from biomass burning, so they are very ubiquitous pollutants, and their net direction is always back into the ocean at this point. With that, I want to switch to the Great Lakes, and this is Lake Superior. And for us, it's an easier place to work with because we have easy access to the shores. We have access to monitoring networks within the lake, so we have a better time figuring out what are the trends in space and in time. And we did that with colleagues from Environment Canada and Ontario Ministry of the Environment, so we had coverage of the whole Canadian side too. And we deployed samplers, different sites, and these are all, you see these little bowls? These are all housing passive samplers. So we made use of a different technology to get a better picture of what was going on. And this is basically one of our passive samplers. It's a strip of polyethylene. And we leave it out till it equilibrates, and that gives us some clues about concentrations and gradients. So just as an example, this is a map of hexachlorobenzene, one of these old pesticides that was banned in the 70s. And you see a remarkably small gradient from maybe 25 picograms down to 9. So a very small gradient suggesting the system is closer to equilibrium. You'll see that the open lake is just as clean or dirty as are the coast. So indeed, the lake had time to move those around and distribute them nicely. And when we then look at both atmospheric and water concentrations, and I listed here maybe a dozen of these old pesticides, and I always show here the air-water exchange gradient. And if you want to maybe focus on the median, in most cases, Great Lake Superior at this stage degasses them back to the atmosphere. A couple of exceptions, most notably endosulfan. Endosulfan was still used as a pesticide in Canada up to 2004, I believe. So it is still dominated by ongoing emissions and volatilization from the agricultural areas. But for most of the others, we see the same effect that we saw in the tropic Atlantic. Lake Superior seems to have the same processes where the compounds are coming back out. So I think that suggests that we can look at the Great Lakes as kind of proxies or model systems that can mimic some of these processes for the big oceans where we have problems of access. We see mostly the coastal oceans as sinks of pollutants at this time, and the open oceans, the oligotrophic regions, as sources. And with that in mind, I wanted to switch to some of the newer compounds. So these are the great perfluorinated compounds that were DuPont and 3M used those quite a lot. They're in Scotchgard, they're in Teflon, they have all these great no-stain properties. And they were recently added to the list of the worst offending man-made chemicals. And the question is a little bit why, and why would we worry about these so much? Well, there's an interesting side effect, that's from the CDC in the US, that 98%, so basically everybody in this room except for one, has these compounds detectable in the blood. So they're very ubiquitous because we use Teflon or these compounds in a range of products and applications. Is there a big concern for human health? Well, there's one study that came out recently from the Faroe Islands. And the islands were chosen because they eat a lot of fish, seals, whales, so a very higher up trophic level food chain of seafood. And Philippe Grandjean from Harvard School of Public Health suggests that the kids show a reduced immune response linked to the presence of these compounds that they had when they were in the womb of their mothers. So it's again the exposure of the fetus that is the problem later on in life, suggesting we should indeed worry about these compounds. More recent studies suggest they are linked to some of the more prevalent, typical conditions of modern societies, early onset of puberties, obesity, you can name it. So probably we've created another set of compounds that we can do research on for the next 10, 20 years till the levels are low enough that we have something else to worry about. The other nice thing about them, that's why I brought them in this session, is that they've been proposed as ocean tracers because these molecules are indestructible, they're highly soluble, and so they should, in theory, follow the ocean currents. That was by Yamashita et al., 2008, and he mostly showed it as a problem of the North Atlantic and probably the North Pacific, whereas the Southern Hemisphere was basically below detection limit, which is a very typical scenario for us to get used to. In more recent work by Jonathan Benskin, in which I was partially involved, you see actually that across the entire Atlantic, you detect these compounds quite easily and even along vast stretches of the Arctic Ocean. On this map, I want to highlight 3 regions that suggest where they are coming from. One is a big plume of Europe. So there's these compounds in water mass that are coming off the European shelf and then moving slowly south before they get diluted by the ocean gyre. You have a hot spot in Narragansett Bay. I'm not sure if this is the only estuary that has this problem or if it's just one of many. And then last, you actually have a southern hemisphere source too. This is the Rio de la Plata. So these particular compounds have moved ahead, and they're now basically a global phenomenon. And if you look at the animals, you'll see highest levels, and these are the scales that we taken off here. So the polar bears, the harbor seals, porpoises, mostly in the northern hemisphere, show extremely high levels of accumulation.
3 minutes left.
Part of the reason why they were banned in the first place. The southern hemisphere cleaner, but you again see here South America, again another hotspot. So there is some concern both on the human side and on the animal side. So to kind of suggest some summaries, I think we see the legacy pollutants are slowly decreasing in the water bodies of the northern hemisphere, but we certainly still have plenty of fish advisories along big stretches of the US coast, and you have the same for water bodies in Europe. But at the same time, we have plenty of new compounds that come in. These include the perfluorinated compounds, flame retardants, or currently used pesticides. So it's not the best picture yet. And the question, of course, how can you improve the situation? And basically, as I said, so dilution will not be the solution in this case. It will have to involve some legislation. And I use the US as an example. When the EPA was founded and the TSCA, the Toxic Substances Control Act, was put into place, all the chemicals that were on the market at the time and on the books of the companies were just grandfathered in. There was no need to retest them. This is a stock of around 100,000 chemicals. And depending on which study you use, a few hundreds to a few thousands of these chemicals have the properties that will make them persistent, toxic, bioaccumulating, and long-range transport. So there are quite a few that should probably be taken off the market just to be safe. The only way to do that it probably is through some legislation. The European Union has done that through a REACH approach, which is debated if it's the right way forward. Right now, the US hasn't found a way forward. There's a Safe Chemicals Act that would do a similar approach, but it hasn't even passed the Senate, and I'm not sure if the House will ever look at it. So the situation is kind of bleak, but legislation would be the only way to prevent more compounds from getting out. And with that, I'd like to thank funding agencies and a lot of people who did all the work. And is anybody ready for questions? Now would be the time. Thank you.
Any questions from the audience? Peter, you had a discussion section.
Okay, just wanted to get some feedback on this session because, as I mentioned at the beginning, this is a bit of an experiment to create a platform for exchange on applied ocean science, on science that has direct relevance for society. Just have to deal with some technical issues here. And yeah, if you see me squinting, these two lights, those of you who were up here speaking know that we are really beamed on. And But so there are a few questions that I would like to get some immediate feedback on, but you also can write to us, to the conveners, about what you would like to see in a future session of that nature, because I hope that we can make that a permanent part of the offering of the Ocean Sciences section, and we would like to adjust that to the needs. So the questions that naturally come up is, A, did you find that exchange useful? Would you prefer to have it more focused on one topic or a subset of topics, or would you like to hear from a broad audience so that you actually get a sense of what your colleagues are doing in other parts of ocean sciences? Would you like to see more stakeholders involved who actually can tell you directly what their needs are, which is a little bit a stretch for HU, but we are willing to make that stretch and change the format so that we can accommodate that. Would you like to stay in the typical HEU format where we have a number of talks, or would you like to see a session split where we, let's say, lead in with a few talks and then have a panel discussion? So there are many things that we can try to do, and we would like to do that so that we meet your interests and what you perceive as your needs and what you think is most useful for your type of work and for how you want to expand that work. Also, if you have ideas how to entrain more of your colleagues who are working on similar issues as you are, all that would be appreciated. So I open the floor for discussion and for soliciting some ideas on what you think you would like to see if we are doing the same thing next year. Anybody? Yes, please.
I'll just say that I found it quite interesting to hear from your speakers their particular problems or challenges that they're dealing with. I think that was very useful for me just to get different perspectives. And obviously, it's very diverse. I'm sure we only touched the tip of the iceberg with the presentations we made today. But nonetheless, I think it is useful to sort of hear how other people, for example, Baja, in comparison to that, the challenges you're dealing with, to the Gulf of Mexico system are very, very different, and yet there's some of the same problems. I think the way to address them, though, is quite different.
Yep.
Yeah, I have a comment, Peter. What we've done here today is much more towards the AAAS meeting format than the typical AGU format. That's with a sequence of longer, up to, say, a half hour even, invited talks, usually on kind of a larger societally oriented theme. And I think our feeling within the Ocean Science section is we'd like to see more of this sort of session here at the AGU meeting, in addition to maintaining the regular, shorter, very specific topical presentations. I think it would make for a richer meeting in the long run.
And if you have ideas on other formats. I mean, we try to bring a speaker in who talks about a societally relevant topic for the luncheon. So we change our format of the luncheon, where we usually just update it on section issues, and we used it for presenting some of the awards. But this time we really want to dedicate it to a scientific talk. And I just learned that the tickets have been sold out. So I hope that this will develop into another platform. But any ideas that you have along the lines of what we have mentioned here would really be appreciated. I think there was, Michaela, did you want to? No? Maybe I just misinterpreted. Yes, please.
We just heard from Jerry Miller about the National Ocean Policy meetings. And if and when there's a research plan that comes out on those, that's destined, if it be the policy that's going to be executed, to be a major driver of the connection of science to society development, but also the funding of science. So I would suggest, I don't know whether you can do, one of the challenges here is
Yep.
It seems to me that would be something that would be more lively and focus on things which I guess we're going to have presidents to be with us for 4 more years. That would help guide discussion and the input of the scientific community.
Yeah, Jerry.
I would just follow that up by saying that, as I remarked at the beginning of my presentation, I think it's really important for our community to be thinking about its work within this sustainability framework. Because you're exactly right. There's so many facets to what we do that have the potential to be societally relevant. But I think we don't do a very good job articulating that yet. So to the extent that we can do the sort of thing that you were just talking about and create a venue here at AGU, in fact, I would say beyond the fall meeting, use other venues within the AGU circle to bring this kind of conversation more to the fore and do it in a way that will engage a broader spectrum of our ocean science colleagues. This session is great, but most of the seats are empty. So while I'm
Right.
encouraged by what's been done so far, we need to make it more visible and create a venue where the conversation will be larger than what we had today.
Yeah, and any ideas on how to do that from your perspective? Because, all of you actually have transcended your, initial disciplinary approach and have ventured into some other aspects of this problem. That would be great. Also, some feedback on why people might come to these sessions or why they might not, in terms of incentives in the system or disincentives in the system, and how we could try to overcome them. Because from the very beginning, I thought this will be a process that will take a few rounds to establish itself, and I just want to make sure that all of us who were involved in that, and by the way, the fourth co-convener is just releasing a tracer in the middle of the Atlantic, Martin Wisbeck, so he couldn't be here. But we all, and beyond the conveners, the section as a whole, would like to learn and understand how we can enhance the dialogue, increase the group that sort of participates in it, and then also in this way have an effect in transmitting some of the information along the lines of what the speakers here outlined into real action and into the solution domain. I mean, that's really what we would like to do. So any last comments? Yes, please. I think that's a very important point, and especially for the fall meeting where we have all these other groups here, and where actually in alternate years when we have an ocean sciences meeting, the ocean science community is here in small numbers. So we will definitely look at that, and if you have specific ideas, we would like to hear about them. Was there another? Raina. No, that's a good point, and we can try to figure out how we can get the speakers together, and we have to think. I mean, a lot of our setup here is not right for that kind of thing, but we have to push the limits and get the right setup. Jim? Yeah, that's, I mean, we clearly, I mean, if this grand challenge develops, then it has a similar structure where you want to have the stakeholders and you want to have the scientists and you want to have that and the funders actually and the politicians and those who make political decisions about the funding in a dialogue, and we have to also figure out how to recruit the right speakers, the audience, and how we present it. So I think there's quite a bit to learn, but I hope that, because we have to close now, I hope that for those of you who were here, it was interesting, it was inspiring to hear from your colleagues who work in different areas but work on similar fundamental issues. And for me, it was really great to hear that broad range of topics and how there are some similarities and some differences. And we will work on that and try over a period of a few years to make that develop that into a platform that will actually drive forward the way we discuss these things and the way we transfer that back into our research. So thanks everybody for all the speakers for your presentations and the audience for listening, and I hope we will have a similar session next fall. Thank you.